It's the most powerful technology of our time. But how does artificial intelligence actually work? We're pulling back the curtain. This is AI Deconstructed.
In our last episode, we made a monumental pivot. We left the world of classical, good old-fashioned AI, a world defined by explicit rules and logic, and stepped into the modern paradigm, machine learning. We defined machine learning, in Arthur Samuel's classic terms, as the field of study that gives computers the ability to learn without being explicitly programmed. We established that instead of a programmer handcrafting every rule, we let the machine infer the rules from data. I promised that this new paradigm, this learning from data, wasn't just one single idea, but a vast field composed of three main families, three different strategies for learning. Today, we zoom in on the single most common, most powerful, and most widely deployed paradigm in all of machine learning: supervised learning. If you've ever wondered how Netflix knows what movie you'll want to watch next, how your email inbox magically filters out junk mail, or how a bank decides whether to approve a loan, you've come to the right place. The engine driving all of these marvels and countless more is supervised learning. The core idea is beautifully simple, and it's one we're all intimately familiar with from our own lives. Imagine teaching a toddler to identify animals. You wouldn't just let them wander through a zoo and figure it out. You'd use flashcards. You'd show them a picture of a lion and say, lion. You'd show them a picture of a penguin and say, penguin. Each flashcard has two parts: the data itself, the picture, and the correct answer, the label. This is the essence of supervised learning. It's a learning process guided by a teacher who provides not just the questions, but also the answers. The goal isn't for the student, our AI model, to memorize the flashcards. The goal is for it to learn the underlying patterns, the concept of lionness or penguinness, so well that when it sees a brand new picture of a lion it's never encountered before, it can confidently and correctly say, lion. This simple, powerful idea is the workhorse of modern AI. So today, we're going to open up the playbook. First, we'll travel back in time to see why this learning from examples approach was such a revolution, a necessary answer to the limits of older AI paradigms. Then, we'll break down the core ingredients of any supervised learning task. We'll explore the two main paths a supervised model can take: sorting things into boxes, a task called classification, or predicting a specific number, a task called regression. We'll learn how to grade our model's performance, its final exam, and discover why a 99% score can sometimes be a failing grade. And finally, we'll cover the most common mistakes and pitfalls, the things that can make even the smartest digital student fail in the real world, from the memorizing student problem of overfitting to the golden rule that every data scientist lives by: correlation is not causation. This is your teacher's guide to supervised learning. To truly appreciate why supervised learning is so revolutionary, we first need to understand the world it replaced. The dream of artificial intelligence is not new. It stretches back to the very dawn of computing. But for decades, the dominant approach to building thinking machines was fundamentally different. From the mid-1950s all the way to the mid-1990s, the field was dominated by a paradigm known as symbolic AI, or as some affectionately call it, good old-fashioned AI. The core philosophy was that intelligence could be achieved by programming a computer with a vast, intricate set of explicit, human-written rules. It was an attempt to encode human knowledge and logic, symbol by symbol, rule by rule, into a machine. Imagine trying to build an AI that can identify a cat using this approach. You, the programmer, would have to create a rulebook. Rule 1, a cat has fur. Rule 2, a cat has 4 legs. Rule 3, a cat has whiskers. Rule 4, a cat meows. This sounds logical enough, But the real world is messy. What about a Sphinx cat which has no fur? The model fails. What about a cat that lost a leg in an accident? The model fails. What about a sleeping cat that isn't meowing, or a picture of a cat's face where you can't see its legs? The model fails, and fails again. For every rule, there are a dozen exceptions. For every exception, you need a new, more specific rule. Very quickly, this approach becomes what computer scientists call brittle. The meticulously crafted rulebook shatters the moment it encounters a situation that the programmer didn't explicitly foresee. This created two colossal problems. The first was the knowledge acquisition bottleneck. How could you possibly interview enough experts to write down all the rules for a complex domain, like medical diagnosis? The second was the combinatorial explosion. The number of possible rules and their interactions would grow to an unmanageable astronomical scale. This brittleness and inability to scale led to periods of stagnation in AI research, known as the AI winters, when funding dried up because the grand promises of human-like intelligence failed to materialize. The world needed a new path forward, and the symbolic end of the old path, the grand finale of the rule-based era, came in the form of a chess match that captured the world's attention. In May of 1997, the reigning world chess champion, Garry Kasparov, arguably the greatest player in history, sat down across a board from an opponent unlike any other, IBM's supercomputer, Deep Blue. When Deep Blue ultimately defeated Kasparov, the headlines were dramatic. It was seen as a watershed moment, a sign that machine intelligence was finally catching up to and perhaps surpassing human intellect. But the story of how Deep Blue won is the crucial part. Deep Blue was not a learning machine in the way we think of it today. It was the absolute pinnacle of the symbolic rule-based approach. It didn't have intuition. It didn't learn from experience in a flexible way. It was a brute force computational monster. Its power came from a combination of complex evaluation functions, programmed by chess grandmasters, and the sheer might of its hardware, which could evaluate 200 million chess positions per second. It won not by being smarter in a human sense, but by exploring the vast tree of possible moves and outcomes with a speed and breadth that no human could ever match. The Deep Blue match is often misremembered as the birth of modern, learning AI. It is more accurate to see it as the glorious death of the old paradigm. It was the ultimate expression of what could be achieved by encoding rules and applying massive computational power. And in its very success, it highlighted the profound limitations of that approach. Chess is a game of perfect information with a finite, albeit massive, set of rules and possible moves. What about problems that aren't so neat? How could you use brute force to identify a cat in a photo, or translate a sentence, or predict the stock market? You can't. The victory of Deep Blue was a catalyst. It implicitly asked the entire field of computer science a question: now what? If programming all the rules, even with immense power, only works for perfectly structured domains like chess, what's the alternative? The answer that emerged, the paradigm that would come to dominate the next quarter century, was to stop trying to handcraft the rules, and instead build machines that could learn the rules themselves from data. This marked a fundamental shift from a knowledge-driven approach to a data-driven one. Instead of telling the machine how to find the answer, we would simply show it thousands of examples of the questions and the correct answers, and let it figure out the how on its own. This is the world of supervised learning. It wasn't just a clever new technique, it was the direct solution to the brittleness and scaling problems that had held AI back for decades. So how does this learning from examples process actually work? While the underlying mathematics can get complex, the conceptual framework is wonderfully straightforward. We can break down any supervised learning task into 5 core components: a playbook that applies whether we're predicting house prices or diagnosing diseases. And to make it stick, let's continue our analogy of a student preparing for an exam. First and foremost, you need study material. Data is the lifeblood of supervised learning. A collection of this data is called a dataset, which you can think of as a giant spreadsheet. Each row in that spreadsheet is a single example. Each example has two parts. First are the features. These are the inputs, the clues, the pieces of information the model will use to make a prediction. If our student is trying to learn to predict house prices, the features for one example, one house, might be its square footage, the number of bedrooms, the age of the house, and its zip code. These are the questions on the test. Second is the label. This is the correct output, the value we want the model to learn to predict. For our house example, the label is its final sale price. The crucial point is that for our training data, we already know this answer. The presence of these known correct labels is what makes the learning supervised. It's the answer key for the textbook. Next, we need the student. In machine learning, the model is the brain that will do the learning. At its core, a model is a mathematical function, a complex collection of internal numbers, often called weights and biases, that defines the relationship between the input features and the output label. Before we start, this brain is essentially a blank slate. It's an empty vessel, structured in a particular way, but containing no actual knowledge. Its job is to find the right internal numbers that best map the questions or features to the answers or labels. Then there is the training. This is where the magic happens. Training is the process of learning. We take our dataset, our textbook full of questions and answers, and we show it to the model one example at a time or in small batches. The process follows a simple iterative loop: predict, compare, adjust. First, the model will predict. It takes the features of an example, like the house's square footage, and makes a guess, a prediction, about the label, the price. Second, it will compare. The model then compares its prediction to the actual correct label from the dataset. The difference between the two, how wrong it was, is calculated. This error is formally called the loss. Third, it will adjust. Based on the size and direction of this error, the model makes a tiny adjustment to its internal numbers, its weights and biases. The goal of this adjustment is to make a slightly better prediction the next time it sees a similar example. This loop of predict, compare, and adjust is repeated over and over, sometimes for millions or even billions of examples. With each cycle, the model gets a little less wrong. It is gradually, painstakingly learning the intricate mathematical relationship between the features and the label. After training, we have evaluation. This is the final exam. A student who just memorizes the practice questions in the textbook might ace a pop quiz but will be completely lost on the final exam. The same is true for our model. The whole point of training is not to get the right answers on the data it has already seen, but to generalize that knowledge to new unseen data. This is where evaluation comes in. Before we started training, we wisely set aside a portion of our data, called the test set. The model has never ever seen this data during its study session. To evaluate our model, we give it the features from this test set, let it make its predictions, and then we compare those predictions to the true labels we had hidden away. This is the final exam. Its performance on this unseen data tells us how well it has truly learned the underlying patterns, rather than just memorizing the training examples. Finally, once our model has passed its exam with flying colors, it's ready to be deployed in the real world. This step is called inference. Inference is the term for using our fully trained model to make predictions on brand new data that has no label. A real estate website could now feed our model the features of a brand new listing that just came on the market, and the model would infer its likely sale price. This is the ultimate goal: to take the generalized knowledge learned during training and apply it to solve real problems. So there you have it: data, model, training, evaluation, and inference. The 5 core steps in the supervised learning playbook. But within this playbook, there are 2 very different kinds of games our model can learn to play. When you set out to solve a problem with supervised learning, you quickly come to a fork in the road. The path you take depends entirely on the kind of answer you're looking for. Nearly every supervised learning problem in the world can be boiled down to one of 2 fundamental tasks: classification or regression. Let's look at classification first. The goal here is to predict a discrete category or a class. Think of it as sorting items into predefined, labeled boxes. The output of a classification model is not a number on a scale. It's a label from a limited set of options. The questions a classification model answers are questions of which kind or what group. Is this email spam or not spam? There are only 2 boxes. Is this tumor malignant or benign? Again, 2 boxes. Based on this photograph, is this animal a cat, a dog, or a bird? Here we have 3 boxes, but it's still a finite, predefined list. The key is that the answer must come from a list of possibilities you've already established. The second path is regression. The goal here is to predict a continuous numerical value. Think of it not as sorting into boxes, but as pointing to a specific mark on a ruler. The output can be any number within a given range. The questions a regression model answers are questions of how much or how many. What will the temperature be tomorrow in degrees Celsius? The answer could be 25, or 25.1, or 25.11. How many dollars will this house sell for? The answer is a specific price. How many points will this basketball player score in the next game? The key is that the answer is a quantity, a measurement on a continuous scale. The core visual difference is the most intuitive way to grasp this. In a classification task, the model is learning a decision boundary. Imagine you plot all your data points on a graph. For a simple spam filter, maybe one axis is number of exclamation points, and the other is mentions the word free. The classification model's job is to draw a line or a curve on that graph that best separates the spam emails from the non-spam emails. This line is the decision boundary. When a new email comes in, the model plots it on the graph, and its prediction, spam or not spam, is simply determined by which side of the line it falls on. In a regression task, the model is not learning to separate things. It's learning to find a trend. It learns a best fit line or curve. Imagine plotting hours studied on one axis and test score on the other. You'll likely see a cloud of points trending upwards. A regression model's job is to draw the single straight line that gets as close as possible to all those individual data points. That line represents the underlying relationship. When a new student comes along, the model uses their study hours to find the corresponding point on the line and predict their score. So, one draws a wall to divide, the other draws a path to follow. This core distinction informs everything from the algorithms we choose to how we measure success. Now that we have the big picture, let's zoom in on classification. While the idea of sorting into boxes is simple, the nature of those boxes can vary, leading to different types of classification tasks. First, there's binary classification. This is the simplest and most common type. The answer is always one of 2 things: yes or no, true or false, on or off. Is this transaction fraudulent or not? Does this patient have the disease or not? Is this email spam or not spam? Next, we have multi-class classification. This is for when there are more than 2 categories. but each item can only belong to one of them. The categories are mutually exclusive. An image might be classified as a handwritten digit from 0 to 9. It can be a 7 or an 8, but it can't be both at the same time. Identifying the species of a plant or the breed of a dog are other classic examples. Finally, there's multi-label classification. This is the most flexible type, where a single item can be assigned several labels simultaneously. Think about tagging a news article. An article about a trade deal between the US and Japan could be labeled with politics, economics, and international affairs all at once. A movie on Netflix might be tagged as action, comedy, and sci-fi. The boxes are not mutually exclusive. Let's stick with our trusty spam filter to see how this works in practice. It's a perfect example of binary classification. The features the model looks at can be incredibly varied. The sender's email address, the IP address it came from, whether the subject line is in all caps, and the presence of certain keywords like free, winner, limited offer, or congratulations. The label is simple: spam or not spam. Where does the training data come from? From you. Every time you or millions of other users click the Report Spam or Mark as Not Junk button in your inbox, you are providing a newly labeled example. You are acting as the teacher. The email services machine learning model is constantly being trained on this massive, ever-growing dataset, learning the subtle and ever-changing patterns that distinguish legitimate mail from junk. So, how do we know if our spam filter is any good? The most obvious metric is accuracy. If it correctly classifies 98 out of 100 emails, it has 98% accuracy. Simple, right? Not so fast. Accuracy can be dangerously misleading, a phenomenon known as the accuracy paradox. Let's switch to a more high-stakes example. Imagine we've built an AI model to detect a rare but aggressive form of cancer from medical scans. This particular cancer only affects 1% of the population. Now, consider a lazy, useless model that does nothing. It simply predicts no cancer for every single patient. What is its accuracy? Well, since 99% of people don't have the cancer, this model will be correct 99% of the time. It has 99% accuracy, but it is completely worthless. In fact, it's worse than worthless. It's dangerous. It would fail to identify every single person who actually has the disease. This is why, for many real-world problems, especially those with an imbalance between classes, we need more nuanced ways to measure performance. To do this, we use something called a confusion matrix. It's a simple table that breaks down a model's predictions into 4 possible outcomes. First, a true positive. The model predicted cancer, and the patient actually has cancer. This is a correct hit. Second, a true negative. The model predicted no cancer, and the patient is healthy. This is a correct rejection. Third, a false positive. The model predicted cancer, but the patient is healthy. This is a false alarm. This is also known as a type 1 error. Fourth, a false negative. The model predicted no cancer, but the patient actually has cancer. This is a misdiagnosis. This is a type 2 error. From these 4 numbers, we can calculate 2 much more useful metrics: precision and recall. Precision is the don't cry wolf metric. Precision answers the question: of all the times the model sounded the alarm and predicted cancer, how often was it actually right? The formula is true positives divided by the sum of true positives and false positives. Precision is all about minimizing false positives. A model with high precision is trustworthy when it makes a positive prediction. In our medical example, a false positive means telling a healthy person they have a life-threatening disease. This causes immense stress, anxiety, and leads to expensive and potentially risky follow-up procedures that were never needed. You would want high precision in a system where the cost of a false alarm is very high. Recall is the leave no stone unturned metric. Recall, also known as sensitivity, answers a different question. Of all the people who actually had cancer, what fraction did our model successfully identify? The formula is true positives divided by the sum of true positives and false negatives. Recall is all about minimizing false negatives. A model with high recall is thorough. In our medical example, a false negative is the worst-case scenario. You tell a sick person they are healthy, and they go home without receiving treatment. The consequences could be fatal. You would want to maximize recall in any situation where the cost of missing something is catastrophic. Here's the catch. You can rarely maximize both precision and recall at the same time. They exist in a natural tension. If you want to increase recall and make sure you catch every single possible case of cancer, you have to make your model more sensitive. You lower the bar for what it considers suspicious. But in doing so, you will inevitably flag more healthy patients as well, causing more false alarms and lowering your precision. Conversely, if you want to increase precision and be absolutely sure you're right every time you diagnose someone, you raise the bar. You only flag the most obvious clear-cut cases. This will reduce your false alarms, but you will inevitably miss more of the subtle early-stage cases, lowering your recall. The choice of which metric to prioritize is not a technical one. It's a human one, based entirely on the real-world consequences of the model's different types of errors. For cancer screening, you would almost certainly prioritize recall. For a spam filter, you might prioritize precision, because letting one spam email through, a false negative, is less annoying than sending an important job offer to the junk folder, a false positive. Now let's walk down the other path from our fork in the road, regression. Here, we're not sorting, we're predicting a specific number. We're not looking for a decision boundary, we're looking for a best fit line that captures a trend. Let's revisit that simple, intuitive example, the relationship between hours studied and test score. If you plot the data for a class of students, you won't get a perfect straight line. People are complicated, but you will likely see a pattern, a cloud of points that trends upwards and to the right. The job of a simple linear regression model is to find the one single straight line that passes through that cloud of points in a way that minimizes the overall distance from the line to every individual point. That line is the model. It has learned the general relationship. For every extra hour of study, the score tends to increase by a certain number of points. Let's build a slightly more complex regression model for a business. Imagine you're opening a new coffee shop and you want to predict your daily sales. This is a classic regression problem. The label, or the dependent variable, is the thing we want to predict, total daily sales in dollars. The features, or independent variables, are the factors we think might influence sales. We could include things like the amount of money we spent on local advertising that day, the official foot traffic count on our street, the day of the week, and a simple yes or no feature for whether there's a special event happening nearby. After training the model on historical data from similar coffee shops, it might learn a relationship that looks something like this in the form of a multiple linear regression equation. Sales equals, say, $10 times the advertising spend, plus $2 times the foot traffic count, plus a baseline of $500. This is a simplified example, but it illustrates the key idea. The model has learned the coefficients, the numbers 10 and 2 that quantify the relationship. It has learned that, on average, every dollar spent on advertising is associated with a $10 increase in sales, and every person who walks by is associated with a $2 increase in sales, on top of a baseline of $500 per day. Now, the coffee shop owner can use this model to forecast future revenue or decide if a new advertising campaign is worth the investment. With regression, we don't have correct or incorrect predictions in the same way as classification. A prediction of $1,001 when the actual sales were $1,000 is technically wrong, but it's a very good prediction. A prediction of $500 is much, much worse. We need metrics that measure the magnitude of the error. The most common way to measure this error is with mean-squared error, or MSE. The intuition is simple. For each day in our test set, we look at the difference between our model's predicted sales and the actual sales that occurred. This difference is called the error or the residual. We then square each of these error values. We do this for two reasons. First, it makes all the errors positive, so that over-predictions and under-predictions don't cancel each other out. And second, and more importantly, it heavily penalizes large errors. An error of $100 becomes $10,000 when squared, while an error of $10 only becomes $100. Finally, we take the average of all these squared errors across our entire test set. That's the MSE. A lower MSE is always better. The main drawback of MSE is that its units are squared. If we're predicting sales in dollars, our MSE is in dollars squared, which isn't very intuitive. So we often take the square root of the MSE to get the root mean squared error, or RMSE. The RMSE is in the same unit as our target variable, in dollars, so it's much easier to interpret. An RMSE of 50 means that, on average, our model's predictions are off by about $50. The choice to use a metric that squares errors, like MSE or RMSE, isn't just a mathematical convenience. It's an implicit business decision. By squaring the errors, we are telling our model that we are much more afraid of one single catastrophic mistake than we are of a bunch of small, minor mistakes. In financial forecasting, a single massive error could bankrupt a company. So a model optimized to minimize MSE will be intensely motivated to avoid those large-scale failures. Another popular metric, R-squared, answers a slightly different question. Instead of asking, how wrong is our model, it asks, how much better is our model than a really dumb baseline? The dumb baseline in this case is a model that doesn't even look at the features, it just predicts the average sales value every single day. R-squared gives us a score, typically between 0 and 1, that tells us the proportion of the variance in our label that is predictable from our features. An R-squared value of 0.75 or 75% means that our model is able to explain 75% of the day-to-day fluctuation in coffee shop sales using the features we gave it, like advertising and foot traffic. The other 25% is due to other factors or random noise that our model can't account for. It's a measure of the model's explanatory power. We've talked about the training process as a loop of predict, compare, adjust. But how does the adjust part actually work? How does a model know which way to tweak its internal numbers to get better? This is where we enter the engine room of machine learning and meet the algorithm that powers almost all of it, gradient descent. First, let's formalize our idea of error. The loss function is the specific mathematical formula used to measure the model's mistakes. For regression, this is often the mean-squared error we just discussed. For classification, it's a more complex function, but the principle is the same. The loss function takes the model's predictions and the true labels and spits out a single number representing the total error. The entire goal of training is to find the set of internal model parameters, the weights and biases, that makes this loss number as small as possible. So, the training problem becomes an optimization problem. How do we find the bottom of the loss function? This is where gradient descent comes in. The best analogy for gradient descent is to imagine you are a hiker, standing on the side of a mountain in a thick fog. Your goal is to get to the absolute lowest point in the valley, but you can't see the whole landscape. All you can do is feel the slope of the ground right where you are standing. What's your strategy? You would feel for the direction of the steepest downhill slope, and you would take a step in that direction. Then, from your new position, you would repeat the process. Check the slope, take another step in the steepest downhill direction. You keep doing this, step by step, and eventually you will arrive at the bottom of the valley. This is precisely what gradient descent does. The landscape is the loss function. The hiker is our model. The direction of steepest descent is a mathematical concept called the gradient. At each step of the training process, the algorithm calculates the gradient of the loss function and nudges the model's weights in the opposite direction, taking a small step toward a lower error. This is the adjust part of our loop, made intelligent. Now, this learning process isn't fully automatic. The data scientist acts as a guide, setting up the conditions for the learning to happen. They do this by tuning hyperparameters, which are settings that control the training process itself. Like the dials and knobs on a complex machine, two of the most important are learning rate. In our hiker analogy, the learning rate is the size of each step the hiker takes. If the learning rate is too large, the hiker might take such a giant leap that they completely overshoot the bottom of the valley and end up on the other side. If the learning rate is too small, the hiker will take tiny, shuffling steps, and it might take an eternity to reach the bottom. Finding the right learning rate is a crucial part of making a model train effectively. And epochs. An epoch is one full pass through the entire training dataset. It represents one complete study session where the model has seen every single example once. The number of epochs is another hyperparameter. If you train for too few epochs, the model will be undertrained. It's like a student who only skims the textbook once. If you train for too many epochs, you run the risk of the model starting to memorize the textbook instead of learning the concepts, a problem we're about to discuss. Building a supervised learning model is not just about feeding data to an algorithm. It's a delicate balancing act, fraught with potential pitfalls that can lead a promising model to fail spectacularly in the real world. Let's explore the most common and critical of these challenges. The single most fundamental challenge in supervised learning is overfitting. This is what happens when a model learns the training data too well. It doesn't just learn the underlying signal or pattern. It also learns every random fluctuation, every bit of noise, every irrelevant quirk present in the specific data it was trained on. It has, in effect, memorized the answers to the practice test instead of learning the subject matter. The consequence is a model that looks like a genius during training, but is a fool in practice. It will achieve a very low error on the training data it has already seen. But when you give it the final exam, the unseen test data, its error rate will be shockingly high. It has failed to generalize. An overfitted weather prediction model might learn a random correlation that on 2 specific Tuesdays in July, it rained, and treat that as a universal law, leading to terrible future predictions. Overfitting defeats the entire purpose of machine learning. Overfitting is one side of a coin. The theoretical framework that helps us understand this problem is called the bias-variance trade-off. It describes the fundamental tension in building a model that is both accurate and generalizable. High bias means underfitting. This is the opposite of overfitting. A model with high bias is too simple. It makes overly strong and often erroneous assumptions about the data. It fails to capture the underlying patterns. This is called underfitting. An underfit model performs poorly on the training data, and also performs poorly on the test data. It's just a bad model all around. The classic example is trying to use a simple, straight line, a linear regression model, to describe a relationship that is clearly complex and curvy. The line is too simple to capture the truth. High variance means overfitting. A model with high variance is too complex. It is hypersensitive to the training data. Instead of finding the general trend, it wiggles and contorts itself to hit every single data point perfectly, including the noise. This is overfitting. Such a model performs brilliantly on the training data, but terribly on the test data, because the noise it memorized doesn't exist in the new data. The example here is using an incredibly complex, squiggly line to fit a simple trend. Here is the trade-off. As you increase the complexity of your model, you typically decrease its bias, so it can capture more complex patterns, but you increase its variance, making it more likely to overfit. The goal of a data scientist is not to eliminate bias or variance completely, but to find the sweet spot in the middle, a model that is just complex enough to capture the true underlying signal, but not so complex that it starts memorizing the noise. Perhaps the most common reason for AI failure has nothing to do with complex algorithms or the bias-variance trade-off. It's much simpler. The data was bad. The mantra garbage in, garbage out is the absolute law of the land in machine learning. An AI model is, and can only ever be, as good as the data it is trained on. Inaccurate, incomplete, or biased data will always lead to an inaccurate, incomplete, or biased model. There is no more potent example of this than Amazon's attempt to build an AI recruiting tool. The goal was to feed resumes into a model and have it spit out the top candidates. To train it, Amazon used a decade's worth of its own historical hiring data. The problem was that, like much of the tech industry, that historical data was heavily skewed towards male applicants. The model learned exactly what it was shown. It didn't learn to identify the qualities of a good software engineer. It learned to identify the qualities of the people Amazon had hired in the past, who were mostly men. The system taught itself to penalize resumes that contained the word women's, as in captain of the women's chess club. It downgraded graduates of 2 all-women's colleges. The algorithm wasn't maliciously sexist. It was just a perfect mirror, reflecting the bias that was already present in its training data. Amazon ultimately had to scrap the entire project. This was not a failure of the algorithm's logic. It was a catastrophic failure of the data it was fed. Finally, we arrive at the most important intellectual pitfall in supervised learning. The models we've been describing are incredibly powerful tools for finding patterns and correlations in data. They can detect subtle relationships that no human ever could, but they have absolutely no understanding of causation. The classic example is the strong positive correlation between ice cream sales and shark attacks. The data is clear. When people buy more ice cream, more shark attacks occur. A supervised learning model trained on this data would become excellent at predicting one from the other. But does this mean that eating ice cream causes shark attacks, or that shark attacks make people crave ice cream? Of course not. There is a hidden third variable, a confounding variable, that is causing both. Hot summer weather. When it's hot, more people go to the beach and swim in the ocean, which increases the chance of a shark encounter. And when it's hot, more people buy ice cream. The two events are correlated, but neither causes the other. A machine learning model has no way of knowing this. It only sees the numbers. It finds the pattern that X and Y move together. It cannot tell you that Z is causing both X and Y. This is a critical limitation. It means that while a model might be a powerful predictive tool, using its learnings to intervene in the world can be dangerously misguided. If a city government, armed with our model, decided to ban ice cream sales to reduce shark attacks, it would be a comical failure. This is why human oversight, domain expertise, and critical thinking are indispensable. The model can find the what, but it's up to us to understand the why. We've covered a lot of ground today, from the grand history of AI to the nuts and bolts of how a model actually learns. As we wrap up, let's distill it all down to a few key pieces of wisdom. First, supervised learning. The paradigm of teaching a machine with an answer key is not just one small part of AI. It is the engine behind the vast majority of the practical, world-changing AI applications we use every single day. Understanding its core logic is understanding how a huge portion of our modern digital world works. Second, this world is fundamentally divided into two tasks: classification, which is about sorting things into labeled boxes, and regression, which is about predicting a specific number. How we measure success for each of these tasks is not a simple matter of accuracy. It requires a nuanced understanding of the real-world consequences of being wrong, forcing us to balance the risks of false alarms against the dangers of missed detections. And third, and most importantly, a model is a reflection of its data. The phrase garbage in, garbage out is not a cliché. It is the first and most important commandment of machine learning. Models will learn and amplify any biases, errors, or blind spots present in the data they are fed. And while they are phenomenal pattern finders, they are naive thinkers, utterly incapable of distinguishing a meaningful causal link from a mere statistical coincidence. Supervised learning has given us incredible tools, from models that help doctors diagnose diseases earlier to systems that protect us from financial fraud. Its power is undeniable, but it is a tool that requires a wise and cautious operator. We've spent this entire episode with a teacher and an answer key, learning from data that is neatly labeled. But what happens when the data has no labels? What if we don't have the right answers to begin with? This brings us back to the garbage in problem. Those labels, the answer key, almost always come from humans. Thousands of workers labeling images, teams of expert radiologists labeling X-rays. This is the great labeling bottleneck. It is slow, it is expensive, and it is a primary source of that human bias we saw in the Amazon example. This enormous cost of creating labeled answer keys is precisely what motivates the other two families of machine learning. What if you don't have an answer key? What if the task isn't to predict a known value, but to discover unknown structure? Next time, we venture into the wild world of unsupervised learning, where the AI's job is not to predict an answer, but to find the hidden patterns in the data all by itself.
You've been listening to AI Deconstructed. Join us next time as we unpack another layer of the technology shaping our future. Until then, stay curious. Subscribe for more.